All right, hello everybody. Welcome back. This is lesson 5. Today we're going to talk about asymptotes and limits associated with them. This is one of the last lessons of Unit 1. Unit 1. After this, we have IVT. So, I don't see why we can't just jump right into it, all right? So, as I've previously defined, the limits as x approaches infinity are not the same as the limit that x approaches c of f of x is going to be equal to an infinity. These are two different things. This defines the end behavior. This also defines the end behavior, but in a different way. This defines a vertical asymptote. So let's just get straight into it. All right. So what are vertical and horizontal asymptotes? You might already know this. You might not. So I'll just define them for you. A vertical asymptote is when a specific graph in a function, let's say this is x equals 1, right? This is when it is impossible for the function to reach that point. Meaning, like for example, like this, right? No matter what happens, this function, let's call this f of x, will never reach x equals 1. It is impossible for that to happen. Right? And horizontal asymptotes are very different. I'm going to maybe if your teacher didn't teach you this before, this might be surprising to you, but horizontal asymptotes can actually be crossed. Something like this could absolutely happen. Because horizontal asymptotes, while not usually crossed, define end behavior. They don't define a clear boundary. Only vertical asymptotes or infinite discontinuities are able to do that. We also call these infinite discontinuities, right? So yeah, that's pretty much the gist of what horizontal and vertical asymptotes are. So now let's talk about their relation to limits. I'm going to draw pretty similar function. Let's say this is x equals 2 this time. Let's go like that. And then let's go with this. This function we will call g of x. So we call the last one f. So we need to create a limit statement that defines what happens when x approaches 2 from the right and the left side of g of x. We need to do this because we need to define where this vertical asymptote is going, right? So we know that the limit as x approaches 2 from the right is signified by this arrow, which is going to infinity. Therefore, this will go to infinity. And we see this arrow on the left going down and down forever. So this is going to go to negative infinity. Again, if you see this arrow, it's indicating that it's going to go on forever. Therefore, we're going to get an infinity. The limit as x approaches 2 of g of x, however, it's a little different. This is negative infinity. This is infinity, right? Those are two different things. Meaning, since they don't go to the same place, it is a DNE, meaning it does not exist. It's similar to what you're going to see in a jump discontinuity. But of course, these are limits to infinity. So yeah, this is incredibly important. Remember that it is DNE. And both of these are also DNE in some cases, in most cases. These are both considered does not exist. But we say DNE whenever traditionally we don't say infinity or negative infinity. All right, so that was pretty simple, honestly. That was a relatively quick and easy thing to do. So I'll give you a few examples. And we'll just go over those together. Give me a moment to pull up these examples for you. So this will be x equals 3. That'll be x equals negative 3. So the function is going to go. The first one, this is how the function will go for the next one. All right. So I'll give you a minute to look at the questions and look at the graphs for a second. We'll call this one h of x, and we'll call this one m of x. All right, and we need to create limit statements to define these vertical asymptotes there, and so we need to show that there is a vertical asymptote in limit format. We need to show that there is an infinite discontinuity. So I'd like you to do that. I'd like you to create a limit statement in order to define these two graphs, h of x and m of x. I'll give you a minute to do that. Please, if you pause the video and then you can see if you got it right after I explain it. All right. So this is the limit as x approaches 3 from the right of h of x is going to be equal to negative infinity, right? Limit as x approaches 3 from the left of h of x is going to be infinity. The limit as x approaches negative 3 from the right of m of x is going to be negative infinity. Excuse me for a moment. Excuse me. Let me just draw that a little bit better. Let's go limit x approaches 3. Negative 3 from the right of h of x is going to be negative infinity. Remember that this plus and minus is indicative of the left and right sides. This should be m of x, my bad. This should be m of x. It's infinity. And that means the limit as x approaches 3 of m of x is DNE. Same thing with the limit as x approaches 3 of h of x. It's also DNE. Because it's not going to the same infinity. Meaning we can't even say it's infinity. We have to call it DNE. Or does not exist. Alright. That was pretty much limits to infinity of vertical asymptotes. So now we have to explain horizontal asymptotes. As we've defined before, they define the end behavior. While not usually being crossed, they can be crossed. Not usually crossed, so let's say not usually crossed, but they can be crossed. We'll draw this graph. This is going to be y equals 2. And we'll draw this function. They can be crossed in specific scenarios. This is important. So, like, for example, a horizontal asymptote at a specific number might not, like, exist due to the fact that, like, okay, for example, the square root function. Let's take the square root function. Square root function. I mean, well, no, let's not take the square root. Let's take the function x squared. So let's say f of x is equal to x squared, right? For obvious reasons, this can never be negative. Does that mean x equals 0 is a vertical asymptote? No, right? Oh, this is different than probably what I'm talking about. My bad. So basically a case where we need to talk about a case where horizontal asymptotes cannot be crossed, or horizontal asymptotes cannot be crossed. And this is going to be usually the case that you see with a function. So let's take a random function like this. Let's say there's some function. This function will be called h of x, and this function will be called m of x. We're just going to reuse function names, all right? So this function h of x and this function m of x are both functions that will never approach that, that will never cross that horizontal asymptote for some reason. The most famous example of this, I just remembered the most famous example of this, so let me just draw it really quickly for you, is probably going to be this, right? And what this is it is the negative natural log function, I believe. Just give me a moment to verify what I'm saying. It is not the negative, it is the, let's just call it it's not the negative log function. It will be it would be something else. Let's just say this is going to be a random function. Let's call this a of x. All right. Let's just call this a of x for now. Yeah, let's not define it as any function. This obviously has a vertical and horizontal asymptote though. And this is going to go to this will never hit 0, but it's going to get microscopically close to 0. So there are some functions that can never equal 0. For example, yeah, this function is actually a great example of a function that can never hit 0. Yeah. And therefore it has a horizontal, but it'll get very, very close to 0. All right, yeah, I think that's a good example of it. All right. Now let's actually talk about horizontal asymptotes and their limits. I know that might have seemed a little bit confusing. We'll probably go over that in the next lesson. Again, so I think we'll probably just go over that section in the next lesson again, so I can explain it a little bit better. But for now, let's just talk about horizontal asymptotes and their limits. So let's say there is a horizontal asymptote at y equals 2. And you want this, you want to define this in words, right? This is actually a great function because it's also got a vertical asymptote. You might recognize this function, yeah. It is obviously the rational function, or close enough to it. Obviously, it's not at x equals 0. Actually, this rational function is what I was talking about earlier. This is a case where the function cannot cross the x-axis. So obviously, it's a good function to use at the beginning, right? So what we're going to start by doing is we're going to start by defining defining the vertical asymptotes, which we know. Actually, wait, no, this is about horizontal asymptotes. My apologies. Let's just purely focus on the horizontal asymptotes. The limit as x approaches infinity, limit as x approaches negative infinity. Remember, horizontal asymptotes define end behavior. They define what it's going to look like at the very ends of the function. We're just going to call this b of x. B of x, b of x, equal to, right? So the limit as x approaches infinity is going to be 2. And this is also going to be 2. That might seem a little confusing, that this arrow that's supposed to go to infinity is not going there. But this arrow is actually defining something different in this case. Since we know that this function is a rational function, obviously we can see by its qualities that it's going to be a rational function. And we can tell that it's approaching this. We can tell that it won't ever cross that horizontal asymptote. So, therefore, we can define the limit as x approaches infinity and negative infinity as 2, since they're both approaching that number. And remember, this is not the same as, you can't like merge this into one thing, remember? Because you're not approaching it from the left and right side. This is a completely different thing to vertical asymptotes. Vertical asymptotes, you're approaching something from the bottom and the top, and you're trying to find a limit as x approaches a particular number, which, I mean, in this case, it would be obviously x equals 0, and you're trying to figure out if it approaches an infinity or a discontinuity, like what's going on. But this purely defines the end behavior, what is happening as x approaches those infinities. I'll give you 2 examples that define both vertical and horizontal asymptotes, and then I'll do one with you, and then I'll actually give you one as homework today. So let's do this. X equals 1. Let's do this. X equals 3. For the homework one, I'll make it a little harder. This should be -5. -5. Just to test you more. And then this will be x equals 2. Maybe y equals 2, my bad. All right. And this will just be y equals 1. Okay? All right, I'll give you like 5 seconds to do this. Pause your screen. 5, 4, I'm going to explain it in 5 seconds, so just pause your screen and do it, and then come back to me after you've done it. By the way, what we're trying to do is define both vertical and horizontal asymptotes in limit form. So that's what I want you to do. I want you to define both in limit form. This is y equals 1. All right. 5, 4, 3, 2, 1. All right. Limit as x approaches 1 from the right. It's going to be of, let's call this function c of x. Let's call this function d of x. I forgot to define that earlier. You can just call the functions whatever you want, though. C of x will be equal to infinity. The limit as x approaches 1 from the left of c of x. It's going to be negative infinity. Obviously defining what that vertical asymptote is going to look like at that particular point. And now we're going to define the end behavior. So limit as c of x approaches infinity and negative infinity. And that's going to be equal to 1 for both. As we can see, that arrow is drawn pretty badly, but yeah, it kind of hits them at the point. All right, so I just wanted you to do that one first. And now I'm going to draw the other one for you. All right. Second. Okay. Right. Oh, wait, that's my bad. That should not be drawn like that. I will fix that real quick. Should be drawn like that. And then it should be like that. All right, and it's your homework to synthesize this problem. I'll probably go over it in the next lesson. But for now, this is your homework, so homework. Just one problem for now. Just starting you easy, right? And I will give you the answers in the next video. All right. Bye, everybody. Have a good day.